Hello and welcome to another video tutorial about FreeCAD. In this video tutorial we are going to discuss how to model inner threads. As an example, we will have a look at a hexagon nut of the size M6, and we will talk about different kind of representation, so to say different kind of modeling, ending up in a swept profile along a helical path and a Boolean cut to get a thread like the threads we have in real life on nuts or other parts. The FreeCAD version we use here is the 0.15 stable release on a Windows 7 64-bit system. When it comes to mechanical engineering, and we have, let's say, a quite complex technical machine of some sort, we have a lot of nuts and inner threads on all parts. But in most cases, you won't see the threads, because if you insert a bolt or a screw or something alike, the thread becomes invisible to you. To save CPU performance, in mechanical engineering, we don't use a representation which shows an inner thread. Remember, we talk about the 3D model. Showing a thread on a virtual 2D sheet of paper is something else. But in mechanical engineering, for a 3D model, we use a representation like this. It's an abstract representation. We have a flat cylindrical inner face. As you can see here in the tree view, the model was done using the part design workbench in FreeCAD. We first made a sketch and revolved it. The sketch contains the inner profile here. It defines the 8 of the screw and the two slopes, the slope here and the slope here. Then there is a pocket operation applied to get the 6 faces which form the hexagon on the outer shape of the model. This kind of representation is sufficient for mechanical engineering. Somebody doing mechanical engineering will have a look at this model and say, okay, we are talking about a hexagonal nut, and maybe he will use the measurement tools in the CAD system to measure the width across flats here to get an idea about the size of the nut. Maybe he will also measure the 8 of the nut to get an idea if you're talking about a nut with normal 8 or reduced 8. But in real life, this person would have to consult, for example, the part list to get additional information about the nut, such as the material, or maybe there is also a surface treatment applied to the nut, something like zinc plating or nickel plating. Of course, there are certain cases when you need an optical representation of a thread. In this case, you could use a model like this. As you can see here in the tree view, the part design workbench was used for pad operation, doing the hexagon faces. And we also did a revolution. If we look at the sketch of a revolution here, you can see we have this zigzag-like profile with a polyline, And if you revolve this, and then do a Boolean common operation, well, at least talking about optical representation, it looks like a thread and doesn't use that much CPU power, and therefore it doesn't use that much file size on your hard disk. Additionally, there might be cases when you need a real thread with all correct dimensions, for example for 3D printing. Then you would use for the inner profile a helix and of course some sort of a triangular sketch being swept along the helix and then doing a Boolean cut on the rest of the shape to get this helix-like shape. I'm now going to show you how to do all of the three models step by step. So let's first close these documents here. Let's insert a new document and make sure that Part Design Workbench is activated. Let's first create a sketch on the XZ plane, applying OK. Let's zoom a little bit to the origin, and in my case I chose by Edit, Preferences, Display, Sketcher, a grid size to be shown of 2 millimeters. So each step here is 2 millimeter. Okay, so let's start the sketch by using the polyline tool and starting on the horizontal axis. Let's first insert a slope like here. Then let's insert a vertical line here, a slope in this direction, horizontal line, slope here, vertical line. Let's go back in a slope to the horizontal axis and then back to the first point of our polyline. If I would have caught here the horizontal axis, the solver would have shown an error message saying this point onto this axis, this point on this axis, and a horizontal constraint is one constraint too much. But in this case, everything is okay. We have an under-constraint sketch with 11 degrees of freedom. So let's first begin with constraining our angles here according to DIN ISO, and we now need an angle of 150 degrees. We also need here an angle of 150 degrees because DIN ISO says that this angle here should be in total 60 degrees, and this slope here can vary between, as far as I know, if I recall correct, 15 and 30 degrees. So let's choose 30 degrees so that this angle here is 150 degrees because horizontal line would be 180 degrees. Okay, let's constrain this angle here to be also 150 degrees. And let's also constrain this angle here to be 150 degrees. Let's choose these two lines here and apply an equality constraint, and also apply an equality constraint on these two lines. Let's choose this point here and the origin and apply a horizontal constraint of 2.5 millimeters. Because with an M6 thread, the inner bore diameter, according to Dean, or to use the newer definition, according to ISO, is 5 millimeters, so the radius is 2.5 millimeters. Also applied to these 2 points, a horizontal constraint of a horizontal dimension of 3 millimeters. That's 6 divided by 2. We apply to these 2 points a horizontal dimension of 4.9 millimeters, and we will pull this line a little bit inwards and apply to these 2 points a horizontal dimension of 6 millimeters. We can then place these dimensions a little bit better for visibility, and we will apply to these 2 points a vertical dimension of 4.7 millimeters. That's it. We have a fully constrained sketch. We close the sketch and apply a revolution for vertical sketch axis. Let's say OK. And we just did the first sketch correctly. Okay, so the next operation is to use the pocket operation to get the 6 hexagon faces on the outer wall of the shape. So let's select the face here, apply a sketch to the face, and let's select the create regular polygon icon to get its help in creating the hexagon. So click on the icon here, select the origin, and let's select a point here. So we have now an under-constrained sketch with 4 degrees of freedom left. So let's select this point here, and let's select the horizontal axis, and we will fix the point onto the axis with this constraint here. So let's repeat the operation with this point here. We then have 2 degrees of freedom left, so we will apply to these 2 points in regard to the horizontal axis a symmetry constraint, and then we will apply to these 2 points a horizontal distance of 10 millimeters. We will then insert a circle from the origin here, and we will click once again here. And remember that we did a radius here of 6 millimeter, so we apply a radius to this circle of 6 millimeter or more. Let's say we use 7 millimeters in this case to get an overlapping for our Boolean cut, which is mostly a good idea. Let's close the sketch. It is fully constrained, and use the pocket operation to say, for example, through all, or I could use dimension of 4.7 or more. Remember V8 we defined with 4.7 millimeters. I click on OK, and we are here complete with the whole model for the first case. So for the next case with cylindrical thread, which I did show you, let's use a different design approach, just to practice modeling in FreeCAD a little bit more. Let's close this document here. Let's create a new document. And we once more use the part design workbench, and in the end we use the part module workbench for our Boolean operation. So first we apply a sketch to the XY plane. We do once more use the create regular polygon icon. We select the origin here. We click here in empty space. We'll apply a fixature constraint from this point to the vertical axis. Let's try what happens if we apply a vertical constraint here. And we still have 2 degrees of freedom left. So we could apply a constraint of this point and the origin being coincident. This would have been the same as applying, for example, symmetry to these 2 points, or these 2 points, or these 2 points. So we have still 1 degree of freedom left. This is the horizontal dimension of 10 millimeters between, let's say, these 2 points. We close the sketch and we pad it to a height of 4,7 millimeters. We choose OK. And we just completed the first step of this model. Okay, so the next step is to draw the sketch, which we will use for revolution. And the last step would be to use the Boolean common operation on both solids to get the resulting shape. So first I'm going to select the pad here, doing a right click and toggle its visibility to be able to sketch a little bit better. When I click in empty space somewhere to deselect everything, I will apply a new sketch, this time to the XZ plane. For reference, just look in the right down corner where the small triad with the coordinate system is always present. And click on OK. So now we will draw once again our sweep profile, our revolve profile with the polyline tool. We will begin on the horizontal axis, doing a slope here, going vertical a little bit here, do one zigzag, being once more vertical here, doing a second time a zigzag, being vertical here, doing once more a zigzag, vertical, now one more zigzag, and now one more vertical, one last slope inwards, and when we have a horizontal line, slope here, a vertical line, slope going back to the horizontal axis, and back to the first point of a polyline. We have our well-known arrow. In this case, I'm going to remove this constraint here by selecting it, and then you can press delete on your keyboard, or you could also, for example, do a right click here on this constraint and choose delete. So the error message is now gone, and we will begin to constrain our sketch. So first thing we can do is select this point and this line here and apply a fixature of a point onto the object. This will cause these two lines to be collinear or inline. We will repeat this operation here, and we will repeat the operation once more here, and once more here. We will tell these three inner lines to be equal, or to be correct, of equal length. We will tell all these lines to be also of equal length. We will apply an equality constraint to these two lines. And we will apply an equality constraint to these two lines. Okay. So now we will use a small geometric trick. We will create a line from this point here to this point here and apply a vertical constraint to this line. We will then choose this line and we will toggle the construction mode, and then we will apply a fixature constraint of this point here on this line here. We will repeat the operation here. We will repeat the operation with this point here, and we will repeat the operation here. So the next thing to do would be to constrain our four angles again. Remember to choose each angle to be 150 degrees. And apply here a fourth angle to be 100. No, we don't need a fourth one. Yes, in this case it would be over constrained, as you can see from the error message. So let's press cancel, and we are done with the angles. So let's then do another geometric small trick. Let's draw a line from here to be on the line here. Let's choose the line to be of construction mode. Let's select the line once more and apply a horizontal constraint. And let's choose this point here of the line, and let's also choose this line here and apply a symmetry constraint. So now we are left with 6 degrees of freedom. So the next thing would be to apply this dimension here, which is also regulated by DIN 13. We apply, in this case, a vertical distance of 1 millimeter. As we see here, the solver overreacted a little bit, so we choose to go back and we apply a constraint once more. Let's first bear for a moment with 2 millimeter. Let's then reduce to 1.5. Very good. And then let's reduce to 1 millimeter. No, still overreacting a little bit. So let's use smaller reduction steps. 1.2 and 1 millimeter. Okay, this looks perfect. Let's reduce the 8 a little bit, and let's apply our first constraint to these 2 points here, the origin and this point here. Let's use a horizontal constraint of 2.5 millimeters as before. Let's make sure that the profile looks right. Sometimes, as you just have seen, the solver overreacts a little bit and finds a different solution, which is unwanted. So the next thing would be to reduce here V8 a little bit, and now apply a constraint to these 2 points, a horizontal dimension constraint of, remember, 3 millimeters. As you can see here, solver overreacted a little bit. Okay, let's go back. Choose these 2 points. Apply a horizontal constraint. Let's bear at the moment with 2.86. Let's change it to 3 millimeter. And for some reason, we are good. Sometimes you need to play around with values a little bit in FreeCAD to get FreeCAD going. So the next thing would be to apply a horizontal dimension constraint to these 2 points of, remember, 4,9 millimeters. As you can see here, once more the solver overreacted a little bit, so we go back, we pull this line a little bit inside. Okay, we choose once more these 2 points, apply a constraint here, and when we do a double click on the dimension, and when we choose small steps to reduce to the value we like to have. Okay. So now we need to select these 2 points and apply a horizontal constraint of, remember, 6 millimeters. When we choose these 2 points to apply our last constraint, and we apply a total 8 of 4,7 millimeters. That's it. We close the sketch. We do a revolution. We say OK. We select the pad, do a right click and toggle its visibility to get both shapes shown here again in the 3D view. We choose Part Module Workbench. We select both of these shapes here, and then we apply the Boolean common operation, or in other words, we make an intersection of the 2 shapes. So now we have the resulting shape here, and this ends the demonstration of the second showcase for optical representation of a hexagonal nut. Now for the third case, so to say, the real thread. I will close this document here. I will create a new document. And I will switch back to the part design workbench. I will begin with the same shape as used in the first sketch. So first I will apply my revolution operation and then my pocket operation. So first I'm going to insert once more on the XZ plane a sketch. I will zoom a little bit here. I will use a polyline tool. I begin on the horizontal axis and I'm doing my revolution profile once more. So once more I delete this constraint here. Let's apply equality. Let's apply equality. Let's apply once more all those four angles of, remember, 150 degree. No, it was this angle here that needs 150 degrees. 150 degrees. And once again 150 degrees. So now I'm going to apply all the horizontal constraints once more. This was 2.5 millimeters. This one here was 3 millimeters. This one being 4,9 millimeters. Oops, the solver overreacted a little bit, so I'm going to go one step back, draw the line inwards a little bit, apply once more horizontal. What do you do here? Let's say 6 millimeters. And then doing a double click and then correcting finally to 4,9 millimeters. Then I will apply here a horizontal distance of 6 millimeters, and here I will apply a vertical distance of 4,7 millimeter. And then I will do the revolution once more. And so we are done with our first step. And now I will choose the pocket operation. So I select the face here once more. I'm doing my sketch, doing a hexagon sketch. Let's say this time I apply a fixature to this point on the vertical axis. I apply here once more vertical constraint. I do apply a coincidence constraint on these 2 points. And I'm applying here a horizontal distance of 10 millimeters. I will then need my circle sited at the origin. And let's say we have a circle once more of 7 millimeters radius to be sure to have an overlapping profile here. We close. We apply the pocket operation through all. And now we have our basic shape. And we are now able to apply our helix sweep and then our Boolean cut on this shape here. Okay, so for the next step, we switch to the part module workbench and we will create a geometric primitive. We choose the helix. We want to have a pitch of 1 millimeter. That's okay. We want to have a total 8 of more than 4.7. Let's say we want to have, to be real sure, 6 millimeters complete 8. And we want to have a radius of, let's say, 2,5 millimeters. We leave the angle at 0 degrees and right-handed is okay. So we create the helix. And now we close this dialog here. We select the pocket shape and we toggle its visibility to be able to draw a little bit better. When we switch back to the part design workbench and we apply a sketch to the XZ plane, say OK. We do zoom here and then we will draw a triangle with its, let's say, base point on the horizontal axis, having here a vertical line and going back to the first point. So now we have to apply equality constraint to these two lines. We have to apply an angle of 60 degrees. And we have to apply a horizontal dimension of, well, we want to have an overlapping. So we apply a little bit less than 2.5 millimeters. So let's try it with 2,4 millimeter to be real correct. And this here should get a horizontal distance of 3 millimeters. And that's it. We have a fully constrained sketch. We close the sketch. And then we go back to the part module workbench. We click an empty space to make sure to have everything deselected. And we choose the utility to sweep. We want to sweep sketch 002. We click once more here in empty space. And the sweep path, we select, we do a multi-select to then press Control on the keyboard on Windows in this case. And we select all these segments here. Say done. We want to create a solid. And we want the beginning face and the end face to be coplanar. So we select the threaded option. We click on OK. And this is our swept profile. We toggle the visibility of the nut here. And then we select the pocket and then the sweep shape. And then we apply a Boolean cut. We can toggle the visibility of the helix. And as you can see, the sketch is also visible. We toggle the visibility of the sketch here. And here we go. This is the complete thread with everything made. Since you may encounter problems in 3D modeling, so to say, you may encounter situations where Boolean operations, especially Boolean cuts, will fail. So let's talk a little bit about troubleshooting in 3D modeling. For talking about troubleshooting, we have to talk a little bit about the background of 3D CAD. With your personal computer, you need a basic operation system to run it. This could be one of the different versions of Windows, or a Linux distribution of your choice, or one of the products from Apple. With 3D CAD, you also need a basic software. It is called kernel. There are well-known CAD kernels on the market, of course commercial ones. Speaking of licenses, the biggest three are the cad kernel, the step kernel, and the ASYS kernel, whose native file format is SAT. FreeCAD is set atop on, as far as I know, the only existing open source 3D CAD kernel, Open Cascade kernel, or in short OCC. This kernel provides FreeCAD the ability to do 3D operations. It's providing the needed mathematics and geometric basis to do that. As other technical products, it has some limitations, and sometimes you need one or two, let's say, small tricks to get everything going. So the best advice is, if you're doing Boolean cuts, be sure to have overlapping geometry. Coplanar faces are not very good for Boolean cuts. It may work, but the operation is also quite likely to fail. A second trick would be to use part primitives instead of revolved or extruded profiles, at least with earlier versions of FreeCAD. I was thinking that FreeCAD, or at least the geometric kernel, was reacting more robust when doing Boolean operations with primitives rather than revolved or extruded profiles. I also encountered one time a situation with an earlier version of FreeCAD that OCC, so to say the geometric kernel, didn't seem to like the fact that the helix and the profile to be swept were lying on the same planes, so in this case the XZ plane, as the revolved profile, which was responsible for the outer geometry. So in that case, I applied via placement a 90-degree turn to the helix and the sweep profile. So the helix and the sweep profile began on the YZ plane, and suddenly the Boolean cut worked. This would be another trick you can use. Another trick would be, well, a little dirty one. We are talking here about mathematics. If 3 minus 3 is 0, well, then we have to cheat a little bit. So maybe you could have success with a Boolean cut if you do a shift the position of one of the two solids you want to cut by a very small amount, let's say 1/1000th of a millimeter. In real life, this is in most cases beyond all accuracy of milling machines, measurement tools, and even beyond normally all accuracy of 3D printing. But shifting positions via placement, for example, of one of the solids by 1/1000th of a millimeter will result in a mathematic result of not being zero, and so maybe the Boolean operation will succeed in this case. So with these tricks for troubleshooting, we have reached the end of today's lesson. I hope that I showed some new things and that you did learn something. Feel free to leave any comments here on YouTube. And well, maybe see you in another video. Bye!